I'm just going to run through a worked example of a manganate titration so that you can see how I would lay it out and where all the numbers come from. So here's our question. Ammonium iron 2 sulfate crystals have the following formula, which is given here, and you can see that the water of crystallization, it's got an N for the number of water molecules, so that's what we're going to be finding out. In an experiment to determine N, gives you the mass of the salt, which is this. That mass was dissolved in to make up 250 centimetres cubed of solution with distilled water and acid. Once you've got that stock solution, it says that 25 centimetres cubed of that was taken for the titration. So this is what we know so far. I've highlighted the part about the salt, about the standard stock solution. So we've got 25 centimetre cubed volumetric flask here, and we have dissolved 8.492 grams of the salt in there, along with some water and some sulfuric acid. Then it says a 25 centimetre cubed portion of that solution was used in the titration. So that's been taken and put in a conical flask, ready for titration. So obviously that 8.492 grams that was in there, you've got much less in there because it's just a small sample. So the next bit of information you're given, I've highlighted in blue. Just try and colour code it to see which numbers refer to which chemicals, but we've got information about the potassium manganate solution now. So the potassium manganate solution, you know the concentration and you know the volume that was required, so I've shown it here in the burette in the redox titration. So that's all the information you're given. So now you need to see what you can do with those numbers and what you can find out. So you're looking for a known concentration and a known volume so that you can start to calculate some moles, and we've got that here. So with titration questions, I like to write out the equation, or at least the part of the equation that we're interested in, so that I can keep all of the working out for one chemical underneath its formula and all of the working out for another chemical underneath its formula. Now what you need to bear in mind is these are not balanced, not at the moment, so we haven't got a full balanced equation, so we can't use it as it is. But this is a redox equation, so you should know how to balance redox equations by doing the half equations and cancelling out anything that's on both sides of an equation. So we need the two half equations for the species that are being oxidised and reduced, so the transition metals. So we've got iron 2+ here taking part in the reaction, and we've got manganate here as well taking part in the reaction. So we need those two half equations. So the half equation for the iron 2+ is nice and simple. Iron 2+ goes to iron 3+ plus an electron. So this is the oxidation. And then for the reduction, it's one of those slightly more complicated half equations, so I'll run through it just so you can see where everything comes from to jog your memory. So we've got a manganese on the left and a manganese on the right, but we've got 4 oxygens on the left and none on the right. So we need to add some oxygens, and you add those in the form of water. So we need 4 lots of water, 4 moles of water, to be able to offer 4 oxygens to balance with the ones on the left. Now we have 8 hydrogen atoms on the right, so we need them on the left, and you add those in the form of H+ ions. So we need some H+ ions, and there's 8 of them, so 8 H+ on the left to balance with the 8 H's on the right. The final thing to add in are some electrons to balance out the charges. So you can see in terms of charge on the left, we have got a negative and 8 positives. So we've got 7+ on the left, and here we've got 2+ on the right. So we need to get this 7+ down to 2+ by putting some negative charge on the left-hand side in the form of electrons. So we will need 5 electrons on the left. So I've just tidied that equation up a little bit so that you can see all of the different parts of it. But you should know those equations anyway, because you do those loads and loads of times when you're looking at redox. So to balance the whole equation, you can see that we've got 1 electron on the right-hand side here, but we've got 5 electrons on the left. So if you're releasing an electron there, but you're needing 5 there, then you'll need 5 lots of the iron half equation. So that needs to be multiplied through by 5, like that. So now we've got 5 iron 2+ reacting with a manganate and 8 hydrogen ions. These will cancel with these, so you can ignore that. This forms 5 iron 3+ ions and a manganese 2+ ion and some water. So you need to get the electrons to match so that they cancel out. And this will give us our mole ratio, so we can now balance this out by sticking in some big numbers. So we need 5 lots of the iron containing compound, and we can leave this as just 1 lot of the manganate. So compared with a normal titration, that's about the only additional step in one of these, is remembering to do the half equations and sort out the balancing of the whole overall equation. Otherwise you can't use a mole ratio. So now let's go back to finding some information that we can use to calculate moles. As I said, we've got concentration here and we've got volume here, so we can work out the moles of potassium manganate that were used in this titration. So I'm going to list what we know under the chemicals and then show how to calculate moles. So that's our information based on concentration. So concentration for the salt is given in terms of mass dissolved in volume, and the concentration that was given for manganate was given in moles per decimetre cubed. So I can just write that down. Now if we look at volumes that were given in the question, involved in the titration were 22.5 centimetres cubed of potassium manganate, which is given here, and 25 centimetre cube sample of the salt solution, which is mentioned here. Now we're looking to calculate some moles. So this looks nice and easy because we've got both of the things we need written in a sensible way, so we can work out moles of potassium manganate. So plugging the numbers into the equation, we have got 0.0003375 moles of potassium manganate. Now we can use our mole ratio to have a look at how much manganate to how much iron 2+, and we can start to talk about moles on this side. So our mole ratio, according to the balancing that we did with the half equations, is 5 of the salt to 1 of the potassium manganate. So our mole ratio is 5 to 1, which means if we've got 0.0003375 moles of potassium manganate, then we have 5 times as many moles of the ammonium iron sulfate solution. So the moles of the solution, the salt solution, are 0.0016875, and remember that's in our sample of 25 centimetres cubed, which is down here in our conical flask. So if we want to work out anything to do with the original solution, which we have the mass and the volume for, then we need to scale these moles up and find out how many moles were in the original solution. So the sample that we used in the titration was 1/10 of the entire stock solution that we've got up here. So if we multiply this through by 10, this number of moles that's in here will become the number of moles in 250 centimetres cubed. So we can just times this number by 10. Okay, so now when we talk about the salt, we can talk about the original solution rather than the solution in the conical flask, because we know that in this original solution we had 0.016875 moles, and we also know the mass because the mass was given at the beginning, which was 8.492 grams of the salt dissolved in that solution. So if we know moles and we know mass, we can work out relative formula mass. So relative formula mass is equal to mass divided by moles. So if we plug those numbers in, we will get the relative formula mass for the salt. So if you plug that into your calculator, 8.492 grams divided by the number of moles, which was 0.016875, you get a relative formula mass for this compound as 503. Now we know most of the things that are in the compound. So we know that there are 2 nitrogen atoms here and 8 hydrogens here. We've got a sulfur here and a sulfur there. We've got iron and we've got 4 oxygens there, 4 oxygens there. We know some of the things that are in it, so we can add up this chunk of the relative formula mass, and whatever's left will be a number of water molecules. So I'll just squash everything up a little bit more so we've got a bit more space on the bottom so that you can see all of the working out on one page. So the relative formula mass of just that part that we know about, everything apart from the water, comes to 284. We know that the whole relative formula mass is 503, so the remainder, if you subtract the 284, we have got 219 left. And that 219 is the mass of all of the water molecules. Now we know one water molecule weighs 18 because it's 16 for the oxygen and the 2 hydrogens, making it 18. So if we divide the 219 by 18, we will find out how many water molecules were in it and therefore find N. So 219 divided by 18 is 12.17, and we can round that to nearest whole number, which is 12. So N equals 12. There's your answer to that redox titration problem. So hopefully the images of kind of what's in your volumetric flask and what's in your conical flask and what's in your burette, hopefully that will help you to see where those calculations come from.